Hey, I'm Joe Fortune and welcome to Mind Dump. Today I'm going to show you how to transfer data from one Arduino to another using only a cheap laser pointer and a solar cell. You can see in my demonstration that I'm sending text across the laser, but for this tutorial we're going to be more general and focus on sending raw ones and zeros. This is known as binary, and everything that exists on a computer is represented in binary. So sending data or transferring a file is merely a matter of sending the sequence of ones and zeros that define it. I'm going to show you how to send the ones and zeros, but it's up to you to be creative and figure out how to represent the data for your project in its binary form. So knowledge you need to have going into this tutorial. You need to have a good understanding of arrays and how to loop through them using for loops. You need to understand how to use the digital write and the analog read function. And as far as electronics go, you need to have the ability to at least blink an LED light. For this tutorial, you're just going to need two Arduinos, a solar cell, this one I salvaged out of a garden light from Walmart, and one of these toy laser pointers. The way this works is actually really simple. When we look at it happening, you just see a brief flash and then all the data seems like it's magically transferred over. If you were to slow it down, what's really happening is the laser is blinking on and off. And what's happening is when the laser's on, that represents a 1. When it's off, that's a 0. Now that has to start a message with a special signal we call the start bit that tells the receiver, hey, start listening for a message. Because if we didn't do this, the receiver would always be listening and this would be interpreted as 0, 0, 0. So we have to tell it, hey, listen up, I have a meaningful message coming. So then at this point, once it receives a start bit, both the transmitter and the receiver have an agreed upon interval. You could think of this like the beat in music. This is the beat at which the transmitter sends the bits, and to the same beat, the receiver receives the bits. It would look like this from the receiver's perspective. So let's say I want to send a message of ones and zeros. I want to send just a single byte to you. So here's a start bit that tells you start listening up, and we start the clock. So it goes 1, 1, 0, 0, 1, 0, 1, 0, and like that. And every time the beat hits, you say, okay, I'm going to take the reading, whatever the value is at that point in time, that's what I'm interpreting it as. So what's the transmitter code actually going to look like? So the transmitter has the byte, and it's got to store the byte, and then it has to have a way to get that byte out to the laser. So let's say we've got the byte 0, 1, 1, 0, 1, 0, 1, 0. Now, how do we want to store this internally? Well, thinking that, we're going to have to operate on each one of these bits individually. And I mean, we're going to have to shoot them out the laser individually. So we're going to have to make decisions based on each individual bit. We don't really want them lumped into a group. It makes the most sense to me to treat them as an array, because then we can loop through it very easily and perform what we need to for each one. So let's think of this as an array. But an array of what? Well, in this case, we're going to use integers, and the reason is because to actually turn the laser on and off, we're going to be using the digital write function, and the digital write function takes an integer as its argument. We don't usually write a number in digital write. We actually write the macros high or low, depending on whether you want the voltage on or off. But the macros themselves are actually integers. So we'll call this array int bits, and that will be of size 8. And the thing to keep in mind is that when we actually initialize this array, that we're not going to be using 0, 1, 1, 0. We're not going to type these integers. We're actually going to use their macros. So let me go back to blue here. So 0 we would write as low, and 1 we would write as high, and then the next one would be high, and so forth. And that's what it would look like when we are initializing the array. Now that we got the concept down, let's go ahead and write the code for the transmitter. So we're going to be doing this on pin number, let's see, laser pin. We'll use 13. And instead of using a variable, I use macros. I feel like it's better C style. And in these tutorials, I'm not going to be using crazy advanced C techniques. I'm trying to make it as user-friendly as possible. However, at the same time, I do want to push good C style a little bit to try to challenge, those of you who are newer to programming to get used to a more
I guess professional style would be what they call it. So I'm going to use a macro instead of a variable. Okay, so setup. What do we need? We don't need the serial monitor, but we do need to make sure we explicitly say pin mode for the laser pin. Declare that as output. Okay, now on our main loop. So I guess it's a good time to talk about what this is actually going to do. What we're going to have the transmitter do is just repeatedly send a bit pattern over and over and over and over, so we can troubleshoot it on the other side. I'm not going to do anything advanced like send text from one to the other. This is just to give you the core fundamentals of how to do this, and then it's up to you and your imagination to take it where you want after this. So let's see, we're going to do an array that we talked about. So we're going to have our array of integers that we're going to call bits, and we're going to, actually let me go ahead and say what pattern we're going to do. I'll do that as a comment. Let's say the bits we're going to do is 0, 1, 0, 1, 1, 0, 0, 1, 0. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Perfect. And I'm actually going to use the macros for digital write, which would be writing this as low, low, high, low, high, high, low, high, low. And the reason I'm doing that is just because it's good practice to use the macros high and low with digital write. You could use zeros and ones. I'm just sticking with this style. Okay, so we got our bit array. And another thing I want to point out is later on when you get more advanced and you want to transfer stuff like text or files, you're not going to have an array of bits. This is just to make it easier for, the guys, girls out there who are newer to coding to see what the process is. Later, you will decompose characters using like bitwise operation and stuff like that. But that's too advanced for this tutorial. We're not worried about that. We're worried about clarity. Okay, so we have our array. We're ready to send the array of bits, and so we need to signal the receiver, hey, ready to send a message. So we're going to send the start bit. So this is our start bit. That's just sending a digital write to the laser pin, sending the high signal. We're going to give it a delay, so it has a little bit of time. We'll give it 10 milliseconds to catch it. And then we'll send another digital write to the laser pin and say, okay, turn it back off. So that's the start bit. And then from here, we can say, okay, let's send the bits. So we're going to have a for loop for all 8 bits. And in this for loop, we're going to say, okay, laser, whether or not I want you to turn on is based on where you're at in the array of bits. So I'm not going to specifically write high or low. I'm going to say whatever is stored at that location in the bits array. As it cycles through, it'll know, hey, I'm either supposed to be low or high. Then we're going to have a delay. This part is very important. This is the delay that has to match the delay in the receiver. This is the beat. This says, hey, every 10 milliseconds, I'm changing the signal. So the receiver has to say every 10 milliseconds, I'm reading the signal. So that way they stay in sync. And then finally, I'm going to put a digital write just to turn the laser off. Just in case, or let's see, not laser pin. Low. And this is just in case through the loop, if the last bit happened to be 1, well, there's nothing else to turn the laser off, and the laser would stay on, and then within milliseconds, the receiver would see that the laser's still on and interpret that as a start bit. We don't want to do that. So we're going to go ahead and just say, okay, once you're done, make sure that the laser is off. And then finally, we'll have this thing fire off once a second. In between, it'll send a byte every second. And that should do it. Let's see. There's always one error, so let's see. Oh, it's a miracle. It compiled. Okay, let's see what it looks like. All right, we're ready to hook up the laser and see what happens. So I'm just going to take the battery pack out. Now, this is actually a really convenient setup. This particular laser pointer. And the reason is because you take a alligator clip like this. Take an alligator clip and it can touch the spring on the inside. It can grab it and it's insulated against the outside metal. And then you just take another alligator clip, no, not that one, and you hook it just to the, so it touches just the inside like that. And then for the button, I just take a rubber band, wrap it around a couple times, give it some tension, and put it over the button. See if I can get that. Just to make sure that button stays on. There we go. Nope. There. Okay. I'm gonna have a wire on the other end of these alligator clips. Okay, so which way goes where? Okay, this is the positive side of the battery. This is facing out, so that means this red side must be the positive lead. So I'm gonna, what LED pin did I say? Let me look up here. That was 13. So I'm gonna put this into 13. And then the other one goes into ground. Where's ground at? Where are you at, ground? There you are. Okay. It's hooked up. Let me upload. Let's see if it works. Uploading. No. Problem uploading to board. Let me make sure I have the right board set. I normally don't write the Arduino software in Windows. I have my other computer I'm used to doing it on. So I'm still getting used to this. All the ports and whatnot are labeled differently. Here we go. Let's try COM5. Okay, uploading. Seems to be working. Uploading, done uploading. And there we go. Look at there. You can see about every second it's flashing. And it looks like a single flash, but that's actually 8 little bits coming through there. It's actually flashing on and off 8 times a second. So now let's conceptually think about what the receiver is going to be doing. So as we traverse the flow of time, so the first thing that happens is we're going to see, or the receiver is going to see that start bit. So there's going to be that start bit. And then there's going to be on, or periods of on and off, depending on the message it's sending. So it may look something like this. And we have that agreed upon delay time. We know what the interval is going to be. Again, that's like our beat. So as soon as we see that start bit, we know start the clock. Boom, 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 boom. And it takes a measurement. These are the 8 measurements it's going to take. And what it does is, so in the first interval, well, not this one. This is the start bit. I'm sorry. In the first interval, it goes, oh, blank. So guess what? That's a 0. First one, oh, there's a laser there. There's a 1. Next one, there's a laser there. That's a 1. Next one, no reading. So that's a 0. Next one, there's a laser. That's a 1, 0, and 1, and 0. I think I forgot to notate the last one. Right, 1, 2, 3, 4, 5, 6, 7, 8. Yep. And that's how, over the course of time, it's going to be reading in whether or not that solar panel has a high reading indicating that the laser is shining on it or not. What I'm going to do now is hook up the solar cell to the Arduino, and I want to start taking analog readings from it, both from the ambient light in the room and with the laser on it. Because these readings are going to make the difference between whether we interpret the reading as a 0 or a 1. We got to figure out what it looks like just normal room lighting versus, hey, the laser's actually shining on the solar cell. So I'm going to hook the positive lead into analog pin A0, and obviously the black is going to go into one of the ground pins. Here on the serial monitor, what you're seeing is the analog reading from that A0 pin. So what I'm going to do is start shining the laser on it and seeing what difference in reading it makes. See, right now this is the ambient light in the room. But there, laser on, off, on, off. So you can see it's making a difference of about 30 units, and the ambient light reading is staying pretty consistent. It was 6, and now it's the highest is fluctuating, seems to be 8, so about 2 units.
So I think it's safe to say that since the laser reading was all the way up to the 30s, that if we chose a number even around maybe 10, say if the whatever the ambient reading is of the room, if it's 10 above that, we can go ahead and interpret that as a 1. Otherwise, anything less than 10, we'll just go ahead and say that's a 0.
All right, let's do the actual code for the receiver now. So again, we need to define our pins, and we've got our solar pin. Let's see, solar pin, and that is analog pin A0. And I think that's all we need for that. We do need to declare it as input in the setup. So we'll have pin mode for our solar pin, and we'll say we want it as input. Also, we're going to need the serial monitor so we can read the bits that come in. So serial begin at the baud rate 9600. Come down here now to the loop. So what do we need? The first thing we need to do is we need to read what the ambient light in the room is. In fact, we should probably do that in the setup and keep track of that as a global variable. Oops. Don't do that. Okay, so I'm going to have int. We'll call it the ambient reading. Ambient reading. I'll just default to 0. And in the setup, we'll go ahead and take the reading. So we'll say ambient reading equals analog read from the solar pin. And that's going to be our base value. And then any deviation of what we agreed on earlier, I think we said 10 units. Any 10 units above that, we're going to interpret as a 1. So I'm actually going to put that up here as a macro. And I'm going to call it the threshold. The threshold. Threshold. Is it 2 H's? Threshold? I don't know. That's how it's getting spelled. Threshold. Defining that as 10 units. So then down here in the loop, what we're going to do is constantly take readings from it. We're going to say, okay, we'll have a reading. And we're taking that from analog. Let's see, analog read from the solar pin. And then we're going to say, okay, is that reading? Is that just ambient light, or is the laser on it? So if the reading, let's see how we're going to do this. If it's there's the threshold, there's the ambient reading. If the reading is greater than the ambient reading plus the threshold, then that means we got the laser. In other words, from this point, we're really, I should say, we're listening for the start bit. We're waiting to read that first laser. So this gets the ball rolling. So if we see that laser. Okay, so from there, we see the start bit. Now we want to enter our loop and listening for those beats. Or taking a reading for those beats, that delay of 10 we were talking about earlier. Okay, so now that we're in here, we're going to do a for loop. So for int I, while I is less than 8, we're doing 8 readings. And what are we going to be doing? We're going to be reading. What are we reading into? Well, that's a good point. I need to make an array to actually read into. So we'll make our array of bits of size 8, and I don't need to initialize it because nothing's going in there right now. We're going to fill it. So what we're going to do is we're going to take 8 readings into bits. So whichever bit we're at in the loop, we're going to take a reading from analog. Analog. Actually, no, we're not. No, we're not. No, we're not. No, we're not. We're going to take a reading from analog that says, in fact, we need a temporary variable for this. Let's see. Int. We can just use reading again. So reading equals analog read from solar pin. Okay, and I'm going to say if, you know what, we don't even need a variable for that, because this is just kind of a temporary thing. We're just going to say if analog read, whatever we read from there. If that is greater than our ambient reading plus the threshold, again, you know, is this a 1? Then we're going to set that, we'll say, we're going to set that bit to 1. So we say bits 8 equal, or I'm sorry, not bits 8, bits I equals 1. Or high, however we're going to do it. I'll just put it as 1 for this. Else, bits I is 0. So basically, if the reading breaks that threshold, if it's 10 units above the ambient reading of the room, we interpret that as a 1. Otherwise, we're going to say, okay, well, that's a 0. Now, after every iteration of the loop, very important, we got to have that delay. We got to have the delay that says, hey, we got to wait, 10 milliseconds in between these. That's the beat in between the readings. Okay. Actually, I got to add on here. I forgot to even output this to the serial monitor. And I did try to compile it, and of course, threshold was spelled differently. Okay, so after we do the reading, we do a full loop of reading these bits. Where's my loop pen? Right here. Okay, let me get rid of some of that space. Okay, so once this is done, we're going to output it to the serial monitor. We want to do each bit. That's 8 bits, so we're going to need another loop for, let's see, int I equals 0 for all 8 bits. And we're going to go to serial print. We're going to print each bit. So we're going to print bits I. And then after the loop, we want to print a new line because we don't want them all on the same line. Just print an empty line or something like that. Okay, we're uploaded, and let's see how it works. And you can see from the serial monitor, it is transmitting. It is consistent, and it is the byte that we sent. It works. I'll include links to the sketches in the video description. This is Joe Fortune with Mind Dump. We're done here.